This lecture will be discussing Poiseuille's law. P-O-I-S-E-U-I-L-L-E apostrophe S law. Now you may recall in the previous lecture on Bernoulli's equation I mentioned that to derive Bernoulli's equation we apply conservation of energy to a fluid and we neglect any friction forces or anything like that might cause energy to be lost to thermal energy or something like that. So Poiseuille's law is where we begin to deal with that, energy loss due to friction forces. The Bernoulli's equation applies to what's called an ideal fluid, and that's just a word that means a fluid with no viscosity. When you have some viscosity, then it's no longer called an ideal fluid, and then you have some energy that's lost essentially to friction, gets turned into thermal energy. The symbol for viscosity is often mu, and basically viscosity quantifies how much a fluid resists motion or how thick a fluid is. So a very example of a very thick fluid is molasses, syrup, and examples of less thick fluids would be like water or the many fluids that we drink that are mostly just water. That has fairly low viscosity, and so it's pretty thin, and that means that Bernoulli equation is a relatively good approximation there. When you have a fluid flowing through a pipe with some viscosity, and there's going to be some in an ideal fluid. Fluid can just slide through a pipe with no pressure. It just flows totally freely through a pipe. But with a viscous fluid, you basically need some pressure. I'll call it over here P2, and there's going to be some pressure over here as well. But what we're going to need is some positive difference in the pressure, P2 and P1, and that difference needs to be positive. P2 needs to be greater such that fluid is being pushed through this pipe. So how much greater? And that is given by Poiseuille's law, which says that the pressure needed is equal to 8 times the viscosity times the length of the pipe through which you are pushing this fluid times the volumetric rate of flow. So remember that is related to the velocity at which the fluid is moving. So basically it's the amount of fluid that you need to push through every second, divided by pi r to the fourth, where r is the radius of this circular pipe. Now, a couple of important things to note about this equation. First of all, it is for the pretty special circumstance of a cylindrical pipe. Okay, not all fluid flow is through a cylindrical pipe, and when it's not through a cylindrical pipe, this equation does not apply exactly. It still, however, does give an idea of what is needed, or what kinds of things affect the amount of pressure needed to push fluid through a constrained space, a viscous through a constrained space. So it's pretty specialized, only for cylindrical pipes. It's also worth noting that basically all the things we've used in this course, all the laws we've used, conservation of energy, conservation of momentum, torques, statics, all of that stuff could be derived from, in a fairly straightforward way, from Newtonian mechanics. And Newton's second law. Now, the mechanics of fluids, especially viscous fluids, are not so straightforward, so it's not possible to just derive this equation in a straightforward way as it has been for most of the equations we've used in the past. So we're not going to try to derive it, but it is, if you ever need it, it's something that you can easily look up. So this is what's called Poiseuille's law. And it's possible to get some kind of intuitive understanding for all the terms in here, right? I can't really explain the 8, but the viscosity, of course, the more viscous, the more thick a fluid is, the more pressure it takes to push it through a narrow cylindrical pipe. The longer that pipe is, the more pressure it's going to take to push the fluid through. No real big surprises here. The faster you want the fluid to flow, the more pressure that you need in order to get the fluid to flow that fast. No surprises here. Now, the narrower the pipe is, the narrower the pipe is, the more pressure you need. If you make R bigger, then because it's in the denominator, you need less pressure. Another important thing to note, this is R to the 4th. So radius is really, really important. Fluid will flow much more quickly through a bigger pipe. If you double the radius of a pipe, then that increases the flow rate of the fluid by a factor of 2 to the 4th, which is 16. Or equivalently, it decreases the amount of pressure you need by a factor of 16, just by doubling the radius. So this power of 4 is really important, makes a big, big difference. And this is, I am told, a question that can sometimes pop up on medical exams such as the MCAT. For example, the question I just answered, if you cut the radius in half, if you use, say, a catheter that's half as wide, how much is that going to slow down the flow through that catheter? And the answer is, if you cut it down by half, then the flow rate is going to cut down by a factor of 16 because of that power of 4. Okay, so just some important things to note about Poiseuille's law. Another thing we should do is we've introduced this quantity mu, the viscosity. We should ask, what are the units of viscosity? All right, so let's take Poiseuille's law and solve for viscosity, and then we can determine what the units are. It's delta pressure times pi r to the 4th divided by mu L Q, wait, not mu down there, 8 L Q. So what are the units of this? Pi and 8 are, of course, dimensionless. From the pressure, we're going to have newtons per meter cubed. From the r to the 4th, we're going to have meters to the 4th. And then down on the bottom, we're going to have some meters. And we're going to have a volumetric rate of flow, which is cubic meters per second. So, let's see. Oh, I made a mistake. Pressure is newtons per meter squared, not per meter cubed. So up on the top here we have meters squared ultimately, so this is going to be some number of Newton meters squared. Down on the bottom, and we'll go ahead and move the seconds up to the top. Down on the bottom we have got meters to the 4th. So this is equal to some number of newtons per meter squared, seconds, And the newtons per meter squared, of course, is a Pascal, so viscosity is often reported as Pascal seconds, SI units of viscosity. Okay. Another important thing to note about Poiseuille's law is that it only applies to laminar flow of a fluid. So what exactly does that mean? That means laminar, if you think of laminar, that prefix, and you think of the word laminate, laminate tends to be putting a layer on something or putting layers on something. So laminar flow is when the fluid flows in layers. So you'll have fluid down at the edge of the pipe that's flowing more slowly, and it's flowing more slowly because it's meeting friction with the sides of the pipe. And then in the middle it flows faster. Now at the edges it flows slower. But the point is it flows in layers. So the layer closest to the edge flows at a certain speed, the layers farthest from the edge flow faster. The layer closest to the edge actually, closest to the edge, the fluid does not flow at all. And then the highest speed is in the center of the pipe. But these layers, basically, they exist. There's not as much fluid moving between the layers. So this is called laminar flow. And when you have laminar flow, you can apply Poiseuille's law. When you have turbulent flow, which is going to look completely different. In turbulent flow, the fluid is not going to flow in layers because it's going to basically be turbulent and chaotic. It's going to flow all over the place and swirl. There's going to be all these little vortices everywhere. And you get turbulent flow when the velocity is much higher. So for slower flowing fluids, laminar flow tends to happen, but once you get too fast, you get turbulence. And when you get turbulent flow, basically the friction forces, the effective viscosity becomes much greater. A lot more energy is lost to heat in turbulent flow because the fluid is being all stirred up and that's generating heat. And with turbulent flow, you cannot apply Poiseuille's law. Okay, we'll do a sample problem with Poiseuille's law now. If you're still studying this, pause. I'm going to blank it. So let's consider blood donation. And the question is going to be, how long does it take? Now, typically in blood donation, a certain volume of blood is drawn, a pint. So we're going to have V, volume, equals 1 pint. And this is drawn through, basically you have a pretty narrow needle. There's a little hole there in the needle. Here's the needle, pretty narrow needle, and short needle. Now, for blood draws, you want to use a wide needle so that it does not take as long. So it's not a narrow needle compared to other needles, but it is connected to some tubing, and the needle is pretty narrow compared to that tubing, and the tubing ultimately connects to a bag. And so the needle goes in your arm. Here's your arm. And here's your fist. 4 fingers. And a thumb. Okay. I'm going to try this again. there's a fist. There's a hand. And basically, you've got some pressure here. The pressure here is blood pressure. The needle is embedded in your bloodstream, and whatever pressure your blood is at, that's your blood pressure. And that pressure is going to be pushing blood through to the bag. And because the bag is sitting in the atmosphere, the blood inside the bag is basically at atmospheric pressure. So the difference in pressure here is the difference between your blood pressure and the atmospheric pressure. Now, something important to note: when you actually get your blood pressure taken, that's not your absolute blood pressure. That is the difference between your blood pressure and the atmospheric pressure. So typical blood pressures are something like 100 millimeters of mercury. Atmospheric pressure is much more than that. Your absolute blood pressure is the atmospheric pressure plus that 100 millimeters of mercury. The 100 millimeters of mercury is the difference. The difference in the blood, in between the blood pressure and the atmospheric pressure. So we'll call that delta P. Now, there's actually two cylindrical pipes that the fluid has to be pushed through here, right? We have the relatively narrow but short needle, and the relatively long but a little bit more spacious tube. So, we're going to consider, basically, we have to apply Poiseuille's law twice to these two differences, to these two cylindrical pipes. Delta P1 is going to be the difference between your blood pressure and the pressure on this side of the needle, and then delta P2 is the difference between the blood pressure on that side of the needle and the pressure in the bag, which is atmospheric pressure. So this total delta P is going to be delta P1 plus delta P2. Now we can apply Poiseuille's law, and to both of these delta P's. So delta P1 is going to be 8 over mu. That's going to be the viscosity of blood. Length of the needle, volumetric flow rate, divided by pi r to the fourth. And this is, so let's see, I'm going to call this length needle, and this is radius needle, plus 8 mu length tube, volumetric flow rate, divided by pi r tube to the fourth. Note that mu is the same in both of these terms. Whoops. It's just the viscosity of blood. And Q is the same in both of these terms. It's the volumetric flow rate, and that's a consequence of continuity, okay? Whatever volume goes in this needle comes out the other end of this needle. Whatever volume goes out the other end of this needle and into the tube comes out this end of the tube. There's only one volumetric flow rate, so there's only one Q. There's only one pi, and there's only one 8. It's the length and the radius that are different. Length and inner radius of the needle, and length and inner radius of the tube. Okay, so let's solve this. Ultimately, what we want to find is we have a known volume. We need a time. And we can use this Poiseuille's law now to solve for the volumetric flow rate. So let's recall that the volumetric flow rate is by definition the volume over time. So the time it takes, which is what we're ultimately looking for, is the volumetric flow rate over the volume over the volume rate of flow. Volume rate of flow, volumetric flow rate, two words for the same thing. All right, so let's start by solving for the volume rate of flow from this equation, and then we'll plug it in here and compute. We can factor out the 8 mu q over pi r, nope, can't factor out the r, and then we're going to have here ln over rn to the fourth, and plus LT over RT to the fourth. And we can now solve for Q, right, and substitute in there. Basically, we're going to get Q. Or, you know what, let's do it this way. This is going to be a little bit cleaner. Let's solve for 1 over Q. And that's going to be 8 mu delta P over pi, length of the needle, R needle to the fourth, plus length of the tubing over R tubing to the fourth. And now we can take both sides of this and multiply by V, and that gives us the time. So what we finally have is time equals 8 mu delta P volume over pi, length of the needle over Rn to the fourth, plus length of the tubing over R tubing to the fourth. Okay, so there's our answer. We now have to compute and actually calculate how long this is going to be, but we've got the equation we need. The challenge now is finding values for all of these quantities and doing some unit conversions. And there's quite a bit of work to do there. But then we're done. And we're already done with the hard part, really. We're done with the physics. So, if you're still studying this, pause now. I'm going to blank it, and we're going to work on finding values, doing unit conversions, and then putting numbers into this equation. Okay, so to rewrite the equation that we just had, that was the time is equal to 8 mu delta P. I'll try to make this a little bit neater. 8 mu delta P times volume divided by pi, and then we had length of the needle divided by radius of the needle to the fourth, plus length of the tubing divided by radius of the tubing to the fourth. Okay, so let's work on all these variables one by one, getting values. 8 is 8, we know what that is. Pi is pi, we know what that is. What about mu, the viscosity of blood? A little bit of Googling will tell you that viscosity of blood in a healthy individual is typically somewhere in the neighborhood of 3 times 10 to the minus 3 Pascal seconds. Varies somewhat. So that takes care of that. You can find it in SI units. how about delta P? Now we talked about this. This is your blood pressure. When you get your blood pressure taken, that's actually what's being measured is the difference between your blood pressure and the atmospheric pressure. And typical values there are about 100 millimeters of mercury. That's the units that they're using there, millimeters of mercury. Now we talked about this funny unit, millimeters of mercury, and how it actually comes from old pressure measuring hardware that was based on mercury and how high the atmospheric pressure pushed mercury up a tube. That's not how your blood pressure is measured anymore, but the unit is used nonetheless. Now the meaning of that unit, in order to do the conversion, we have to use basically Bernoulli's equation told us from the previous lecture that the difference in pressure was equal to rho g h. The density of mercury is about 14 grams per cubic centimeter, 14 times more dense than water because it is a metal. And so we need to convert that to kilograms per cubic meter, SI units. So that's 14. To get it to cubic meters, we have to multiply by 100. That's the conversion from centimeters to meters. But we have to cube that because it's cubic meters. And we have to divide by 1,000 to convert the grams to kilograms. So this is now in kilograms per meter cubed. So we'll put that in for rho, 14 times 100 cubed over 1,000. And then we need G. G is just 9.8. And the height being 100 millimeters, if your blood pressure is 100 millimeters of mercury. So that is 100 millimeters is 10 centimeters or 0.1 meters. And that will give us the blood pressure in pascals. So let's put those numbers in. We get we had 14 times 100 cubed. Autocomplete is happening because I checked this earlier. Great, we get 14,000 pascals, approximately. Oops. That's our blood pressure. Volume. Volume was a pint. You can use Google to find the conversion factor to cubic meters, and that turns out to be 0.00047 cubic meters. Okay. A cubic meter is huge. If you just think about what a meter is and now make a cube that has a meter length, width, and height, is huge. So pint is a very small fraction of a cubic meter. Tidy up that zero a little bit. And what's left? This was the hardest part, all of these dimensions. So I had to do a lot of searching around on the internet and actually go into the specs from medical supplies companies' websites, and found some information on this stuff. The needles, typically for blood donation, you use 16 gauge needles. And 16 gauge needles have an inner diameter of roughly, I believe it was 1.2 millimeters. So the radius is that divided by 2, or 0.0006 meters, converting everything to SI units. Radius of the tubing. Had to Google around to find some specs on some IV tubing, and that turns out to have an inner diameter of about on the order of 2 millimeters, so the radius then is on the order of 1 millimeter, or 0.001 meters. And I had some help from this from our lab manager, who's more familiar with this stuff, so much appreciation for that. The length of the needles, again, had to go into like medical supplies companies' catalogs and found that 16 gauge needles, a typical length was 1.5 inches. Converting that to meters is 0.038 meters, about 4 centimeters. And the length of the tubing, well, I don't know, but it's not always going to be the same necessarily, but roughly it's about 1 meter. As a rough estimate, that'll do. It's not much, it's not a whole lot less than 1 meter. It's not like 10 centimeters, it's not like 10 meters. So that's a decent rough estimate. A lot of these things are rough estimates. For example, blood pressure, obviously not the same for everybody, and we're using 100 millimeters of mercury. Also, blood pressure is not constant, right? You have two blood pressures. One when one is a maximum amount of blood pressure, and one is the minimum amount of blood pressure. As your heart beats, the blood pressure, every time your heart beats, it cycles up and down. Okay. So, those are all the numbers we need, and we're now ready to substitute that in. So we had 0.00, you can see Google auto-completing again because I double-checked this before, 0.0047 times the 8 from Poiseuille's law times the 3 times 10 to the minus third, that was the viscosity of blood, divided by pi, divided by the, I made a mistake. I made a mistake earlier. The blood pressure turns up in the denominator. I'm glad that autocomplete came up because it helped me, it allowed me to identify that mistake. Okay. So just a simple algebra error. You should be able to spot it on the previous slide. Divided by, what did we come up with? 14,000 pascals for the blood pressure. And then this is all times the length of the needle, which was 0.038, divided by the inner radius of the needle, 0.0006, and then that's raised to the power of 4, plus 1, the nominal length of the tubing, divided by the inner radius of the tubing, 0.001, 1 millimeter, that is, raised to the power of 4. Okay, we've got an answer. Let's divide this by 60 to get ourselves an answer in minutes. And we find that the answer is about, if we round to the nearest minute, it's 5.5 minutes. If we round to the nearest minute, it's about 6 minutes. Now, this is a rough estimate. A lot of different factors can change this somewhat. Recall things we've already discussed. We used a nominal blood pressure of 100 millimeters of mercury, but that's not everybody's blood pressure, and for that matter, blood pressure, again, it cycles. There's a maximum blood pressure and a minimum blood pressure that your blood pressure is cycling through every time your heart beats. And Not everyone's blood viscosity is the same. That can be significantly different. And the length of the tubing was another estimate we made. That's not always necessarily going to be 1 meter. There's some other variables that can get in and change this. For example, a lot of times when drawing blood, they'll have you clench your fist. That will increase your blood pressure slightly. Sometimes a tourniquet is used to increase blood pressure slightly and increase the volume rate of flow. And not always the same type of needle is used. When I was gathering information about this, typically pretty big needles, 16 gauge needles or relatively big needles, are used partially to increase the rate at which blood flows, because 6 minutes is a long time already to have people sitting there. So a 16 gauge needle is a pretty big needle for that purpose. It also actually reduces the forces, the stresses exerted on the blood as it's rushing through the needle, and that's basically preserves the blood a little bit better. But not always the same type of needle will be used, not always the same gauge, not always the same length. So 6 minutes is a rough estimate, but it's pretty representative of how long it takes typically to draw blood. Something like 6 minutes could be somewhat more than that. And it's all because of Poiseuille's law. It's all because of viscosity of blood and the resistance of that viscous fluid to flowing through a very narrow, constrained needle and tube. Okay, so that's Poiseuille's law, an application to a pretty comprehensive problem. Remember, as I mentioned before, I've heard that a number of multiple choice medical tests will often ask just about the basic variables that show up in Poiseuille's law. The fact that radius appears there to the 4th power is really important, because that's why it's so important what gauge of needle you choose and what inner diameter of IV tubing you use, because that really, really strongly affects the flow rate. As I said, just doubling the inner diameter increases the flow rate by a factor of 16, which is huge, and worse, cutting down. If you use an inner diameter half of what we used here for this problem, then you'd be sitting there for 16 times 6 minutes. So that is an important thing to know about that 4th power, and that it also depends on the length of the tubing, and the difference in pressure, the amount of pressure being used to push fluid through the tubing. Okay, next one we'll do a more comprehensive problem in fluid mechanics involving Bernoulli's equation and Poiseuille's law.